Welcome to Session 1 of a three-part Mathcation Fluency series developed by the Teaching and Learning Collaborative. TLC is a nonprofit organization that creates innovative resources and professional development initiatives for teachers in math, science, and computer science. We are excited to dive into numerical fluency with you. We can't wait to hear your seaside stories. We'd love for you to share your experiences as you dive into fluency and splash towards understanding. We would love to see pictures of your Mathcation experience. You can share these with us via email or Twitter. Please be sure to tag us at Connect to TLC and use hashtag TLC Mathcation. You can also follow us on Facebook and include us in posts. We can't see your personal posts, but if you share a post on our page or tag us, we can share it too. Plus, we have a few special surprises in store for pictures, tweets, and posts. If you don't want to share on social media but still want to share ideas, please contact us via email. Contact information can be found in the SMORE newsletter you received.
As we get ready for our Mathcation, it is important to remember a few travel considerations to ensure a great experience for all passengers. Just like a message in the sand, you will have opportunities to communicate during your Mathcation. This will be a time where you are reflecting on your instruction or writing a justification for a problem. These experiences are an important part of the learning process. Research shows that when teachers are engaged in tasks or activities that students experience, the teacher knows how to best support a range of learners and to anticipate student thinking and strategies. We will also be using and discussing the importance of representations. When solving problems, it is important to represent thinking as a student might solve it. Consider the various representations and use virtual manipulatives. If you forgot to pack these, don't worry, we have packed them in your journal. Most importantly, we hope you have fun while learning with us and make new connections that you can take back to your students at the end of your trip. And as always, if you need us during your Mathcation, please reach out. So let's get ready to sit back, relax, and get ready for your Mathcation to begin.
Before we travel to our first destination, let's take a moment to reflect on the educational flight you've already taken. How would you define fluency? What comes to mind when you think about a fluent student? What about fluency instruction? Go ahead and pause the video now, pack up and surf over to your digital journal to reflect on the prompt. When you're finished reflecting, come back and join us for some fun in the mathematical sun. Welcome back, Mathcationers. When you're on vacation, do you prefer to go with the flow or have a detailed agenda? Either way, you'll have the best of both worlds on this Mathcation. We have thoroughly planned the agenda for you, and you get to sit back, enjoy the waves, and surf along with what we have planned. Throughout our sessions, we will be focusing on 9 pivotal understandings for developing numerical fluency. These are essential components to developing numerically fluent students. While we won't go in order, we will be sure to give a great overview of each understanding. So whether you're someone who dips their toes in the water first or someone who dives right in, we are ready to get started on our fluency Mathcation.
As you listen to the sound of the waves on our Mathcation and learn about fluency, let's imagine listening to a book on tape. And as you listen to the story, think about visualizing what is happening. And of course, our book, our story, it's all about story problems. As I read the story problem, listen to what is happening and try to visualize the story. During this time, do not write any information or try to solve the problem. Are you ready? While on a week's vacation, Lola took a walk on the beach each day to collect shells to make picture frames. On Thursday, after her walk, she counted all of her shells to see if she had collected enough shells. She had 48 shells in her buckets. Each picture frame takes 14 shells. Lola wants to make 5 picture frames. Does she have enough shells? Show your thinking. I'm going to give you a moment to think about these questions as they relate to the story problem I just read. Now I'm going to read the problem a second time, and as I read the problem, visualize the story again. Afterwards, take a moment to represent the story using counters, virtual manipulatives, or create a drawing. If you left your manipulatives at home, don't worry, there are a few packed in your digital journal. While on a week's vacation, Lola took a walk on the beach each day to collect shells to make picture frames. On Thursday, after her walk, she counted all of her shells to see if she had collected enough. She had 48 shells in her buckets. Each picture frame takes 14 shells. Lola wants to make 5 picture frames. Does she have enough shells? Show your thinking. You might be wondering, why was the story problem read aloud? Or, I wish I could have seen the problem again. You may have even pushed rewind to listen to the problem a third or fourth time, thinking you missed some important information. Well, reading a story problem aloud multiple times is an instructional strategy that encourages modeling and enhances sense making. Reading a story problem aloud for students without the story in front of them provides students all access to the mathematics at hand. It allows entry points for students who may struggle to read while encouraging those who always compute first with a procedural understanding to think differently about the problem-solving process and to justify their thinking visually, which often is difficult for students with procedural understanding. When a story is read aloud, students must visualize and make sense of the problem by creating a model, drawing, or even acting it out. This allows students to move beyond looking for keywords and finding the numbers and operating without understanding. Instead, students are unpacking the problem to make sense of mathematics while using strategies, manipulating quantities, and building flexibility in their thinking with number relationships. Reading story problems aloud provides an opportunity for students to engage in several different ways. When we think about building relationships, this encourages all students to make sense of the problem, model what is happening, and deepen conceptual understanding. It also allows them to see relationships and make new mathematical connections. When a story problem is read aloud, students are building a story or an image in their mind. In doing so, they are making sense of a problem, allowing them to make decisions on how they will solve that problem, what tools they might use, how they might count, and how they might represent their thinking. All of these allow students to bridge concepts, build mathematical ideas, and foster curiosity. When students build their model before symbolic representation is created, they step away from their procedural understanding. The model dictates their thinking and how it is represented mathematically. This allows for deep learning to occur as students connect visual representations with symbolic understanding. As you implement this strategy in the classroom, you may have students ask questions about the problem. For example, they might say, "Can you tell me how many shells did she collect again?" Or, "How many shells does one frame take?" Or you may even have students ask, "She wants to make how many frames?" It's recommended that when you read that you should be rereading the entire problem and not just answer their question. This allows students to make sense of the problem on their own with their own ideas and intuitive problem solving skills. Additionally, this alleviates students from the mindset that you are the answer giver and puts it back in the hands of them as mathematicians. When we pause and reflect on the importance of modeling for all students, it's important to remember modeling can look different and that the tool that is used can showcase different strategies. Those strategies are what helps us support students to become more efficient, accurate, and flexible in their thinking and understanding. It is through models and strategy development that students build a conceptual understanding, make connections through relationships, and in turn support the development of fluency. Take a moment to read this quote. As students construct a model for problem solving, it is constructed as they are making sense of a problem. A model should not be constructed after a student has computed. When a student constructs a model after they solve the problem, more often than not, the model is not a representation of how they solved the problem numerically. This is particularly evident when students have a procedural understanding. A model often uncovers the how and the why of mathematical relationships and ideas. When we think about when and where procedure should take place in instruction and how it correlates to models, consider these ideas from the research of Carpenter and Levi. In just a moment, you will pause the video, pack up, and head over to your digital journal. There, you will find a link for your student work samples. As you look at the student work, pay attention to the strategies, relationships, and different models students use. Spend about 10 minutes on this excursion, and then we will see you back here. Welcome back, Mathcationers. You may have noticed that the story problem was on each of the student work samples. It is important that in our instruction, we provide a balance in which problem types are given to students. Here are a few ideas for how these problems may be implemented. When looking at the student work, you saw a wide range of models used to make sense of the problem. Although students may have used similar models, the strategies that they used to solve the problem varies between these categories. Let's take a closer look at each of these categories to better understand how students solve problems and what this means for fluency, development, and understanding. In just a few moments, we are going to take a deep dive into the importance of counting in fluency development. So let's take a look at some student work from the task to unpack how they used counting to support the development for fluency understanding. Several students used counting single objects as a strategy to solve the problem. However, they used counting in very different ways. For example, this student counted all 48 objects and then went back and recounted to determine how many frames would be made. This student used counting all as their strategy. Another counting strategy used was counting on. Counting on or counting down or backwards can be difficult for students because they have to coordinate two separate counts when counting. Additionally, they have moved beyond counting all objects and now understand that a specific number is representing a quantity or sequence of numbers without the act of counting. For example, here, the number 14. As you can see here, the student, although was on the number 21, for example, when they were counting, this number and quantity is also represented as a part of that 14 shells. So here the student was not only knowing that they were on counter 14, but they were also trying to tag that as to counter 21 as well. Another counting strategy students use is using tens and ones and counting all of them as ones. Here, students may build a quantity accurately. However, when they go to manipulate or use the quantity, they use it as a set of ones. Often, students can build a number, for example, 48, as shown here. However, they did not know how to apply place value understanding to solve the problem or to manipulate the quantities. This type of counting is seen in students who often have a procedural understanding of addition and subtraction. Students here see tens as ones instead of sets. Several students used the concept of skip counting to make sense of a problem. Skip counting is crucial for students' conceptual and fluency development of facts. Students should be able to use skip counting reasoning beyond pictorial representations and through verbal reasoning. When students skip count, you want to consider how students are using and counting place value units. This is an indicator of their understanding and how they can flexibly manipulate quantities, which impacts their fluency understanding. Let's take a look. Here, this student skip counted all of the tens and then some of the groups of ones before counting on after 12. When solving this problem, the student skip counted the tens separately and then skip counted the ones 4, 8, 12. This is the first understanding students use when learning to count place value parts. It is this understanding that allows students to see the quantities and how they can be counted in a variety of ways. Let's take a look at another student's thinking to see how the relationship of skip counting, place value, and fluency development could look and sound differently. When solving the problem, this student started at 48 and counted back by groups of 10s. This student shows a more sophisticated understanding of counting since they counted in the middle of the decade by counting 48, 38, 28, 18, 8. This type of counting sequence indicates students' ability to understand the patterns in the number sequence, allowing them to become fluent with decomposing by place value parts. Often we see students using the make 10 strategy to get to the nearest 10 before operating. This strategy can sometimes require more calculations, leading to opportunities for more errors. Instead, if students used the mid-decade strategy as shown here, their thinking would be more efficient, accurate, and sophisticated when using skip counting as a strategy. Mid-decade counting allows students to add and subtract quantities more fluently because they apply patterns and flexibility with numbers. Notice that although both students engaged in skip counting with place value, they used other models besides place value blocks to show their thinking. It's important to remember that place value blocks are a tool, not a strategy. Skip counting is the strategy, whether it was an open number line or using the place value blocks. Skip counting is a foundational skill that is a necessity for students to engage in, as they conceptualize the relationship between quantities and operations in order to master addition and subtraction facts. Several students use what is called a derived fact. A derived fact is a fact you know automatically and can use it to help you solve an unknown fact. Often, some of the first derived facts students know and use are doubles, make 10, or make 5 facts. Additionally, students often use a derived fact when using the commutative property. Research supports that allowing children plenty of time to use, discuss, and reflect on derived fact strategies without rushing to memorization has several long-term benefits when building conceptual understanding. Here you can see this student used several derived facts to justify how they counted and represented their thinking on the open number line. These facts include 10 plus 4, 4 plus 4 equals 8, and 6 plus 4 equals 10. This excursion through story problems and looking at student work allows us to zoom in on the pivotal understanding everything begins with counting. Counting allows students to apply numerical relationships in various situations. As this is developed conceptually, student thinking and reasoning will become more efficient. When considering how fluency is supported, it is important to remember that counting is a critical component to fluency development and number sense. As this pivotal understanding states, counting is at the foundation of students' development and understanding of numbers. Students must be able to understand the counting sequence, conceptualize quantities, and understand how to visually manipulate those quantities in a variety of ways that is helpful to them, the problem solver, when solving problems, all of which are building blocks for numerical fluency. It is through this understanding of counting that all strategies are built on and understood conceptually. As students develop as counters, they become efficient, notice patterns and relationships, and are then able to generalize these ideas as rules. As counting becomes more sophisticated, students' strategies and their ability to apply this understanding will become more fluent over time. Often, if students are struggling with the understanding of addition and subtraction concepts, revisiting their counting is a great place to start. Consider, how do they subitize or unitize? Or are they able to compose and decompose numbers? How might a student hold a quantity in their head and manipulate it? Can they count in a variety of ways from various numbers? All of these ideas are not only aspects of why counting is a critical component to numerical fluency, but also how counting is the understanding of many of the pivotal understandings you will learn during your Mathcation. Counting is much more than tracking objects, understanding one-to-one correspondence, and having rote memorization of the counting sequence. Although these are aspects of great counters and some of the counting principles, the role of counting in mathematics is much, much more. Research has shown that we need to move beyond traditions of counting and skip counting and assume that students get what happens beyond 50 or 100 or even 1,000. Students need ample time and varied experience with all types of numbers and many different ways to support them in this critical mathematics sense-making that is done through counting. Counting allows students to apply numerical relationships. As this is developed over time conceptually, students' thinking and reasoning will become more efficient, accurate, and flexible. Counting, although may only appear to be a kindergarten standard, all aspects of counting, such as skip counting, using counting with place value parts, decomposing and composing numbers, and understanding concepts such as more and less remain an important aspect across all K-5 learning and standards. Counting is fundamental to learning mathematics. It supports the development of deep understanding of numbers, provides a core foundation for place value, supports how numbers are composed and decomposed, and how quantities are related to each other. When counting is deeply understood, this allows students to operate in powerful ways, which ultimately impacts students' fluency. Counting is an intricate process that requires the coordination of skills and knowledge, and that is developed over time and continuously challenged as number range increases and operations change. Now that we have spent some time analyzing student work and discussing counting as it relates to fluency development, take a moment and consider how student work samples from the task represent aspects of fluency, understanding, and development. Or what might you be thinking differently about in regards to student thinking and understanding? Later on your Mathcation, Chrissy will elaborate on the importance of place value in the development of numerical fluency. When she does, consider the relationship and role counting has with place value understanding in fluency development and what this means for student learning experiences as they work towards fact fluency. So in just a moment, we are going to pack up and head over to our digital journal. There, spend about 10 minutes during this next excursion responding to the task that is a continuation to the problem that was read aloud. When solving, it's important to build your model first and then represent your thinking with numbers. Additionally, we are going to encourage you to not use the standard algorithm while you solve the problem. Instead, consider how you can use numbers to represent your thinking from your model. If you left your manipulatives at home, don't worry, there are a few packed in your digital journal. Welcome back, Mathcationers. During your excursion, you may have had many questions, such as, does the vacation start on Saturday or Tuesday? Could the week start on a different day? How many shells did she count before or after her walk? Did she collect some shells on Thursday? Are there days that she skips collecting shells? Or does she count shells the day that she arrives or the days that she leaves vacation? What does she do with the broken shells? Does she put them all together to make a whole? Or does she collect the same amount of shells for more than 2 days? Are there more than 2 buckets with the same number of shells? All of these are fantastic questions. And you might have even had other ones that were not discussed. Sometimes students have questions that are not answered by the problem. In this situation, Ask students to discuss with a partner or determine what they think and leave it open-ended. This will allow students to have multiple different solutions, processes, and reasoning. These types of problems not only support fluency, but also classroom culture and promotes mathematical mindsets in your students because they are engaged in the problem-solving process and making sense of problems for themselves. The important idea to remember is that this problem allows for additional questions, multiple solution pathways, and opportunities for you as the mathematician to make sense of the problem. In doing so, you are able to be the decision maker, which provided an opportunity for you to reason and justify your thinking. Most importantly, this activity activates excitement and engagement for all students as it is driven by curiosity and the relationships and patterns while building numerical fluency. When implementing problem-solving activities or tasks, it is important that students are able to engage in these ideas. As a facilitator of student learning, encourage students to ask questions and respond with additional questions that push their thinking forward. This allows students to reason about what makes sense, discuss ideas with peers, and take risks. It is during this time as students construct mathematical ideas, notice patterns, and apply understanding of number relationships that fluency development is supported in the classroom. Like shells at the beach, there is a difference between word problems and problem-solving activities or tasks. The problems you just solved were problem-solving activities. Let's take a deeper dive into how these problem types are different. Students must have opportunities with both types of problems, and there must be a balance of these in your instruction. Both problem types are at the heart of students' fluency development, and they should be where instruction starts, not where it ends.
So, for our sessions, we will focus on numerical fluency as it is defined in the book Developing Numerical Fluency by Patsy Cantor and Steve Leinwand. If you're familiar with the book Principles to Action by NCTM, you're probably also familiar with the term procedural fluency. Numerical and procedural fluency are not exactly synonymous. Some important points to note is that both are built on conceptual understanding. And as you work through numerical fluency, students will begin to develop and use procedures that work for them. Students need many diverse experiences to develop both numerical and procedural fluency. Computational fluency is described as the ability to compute with accuracy, flexibility, and efficiency. Computational fluency is developed over time and is not a fixed ability. It grows and develops through ample opportunities to practice and discuss strategies. Numerical fluency is the ability to compose and decompose numbers flexibly, efficiently, and accurately within the context of meaningful situations. It is important to note that procedural fluency is not reached through teaching and practicing rote procedures. The goal over time and through many experiences is for students to become procedurally fluent, which is achieved through a conceptual understanding and numerical fluency. Note the relationship shown here between accuracy, flexibility, and efficiency, and numerical and computational fluency. We can see that fluency is directly tied to conceptual understanding of numbers, place value, and operations, not simply to the rote memorization of procedures. So we can say that students will not achieve procedural fluency without first developing numerical and computational fluency. We'd like you to keep the ideas just discussed in mind as we continue to build our sandcastle of knowledge. So while on the beach, it is not uncommon to see children and adults alike building sandcastles along the shoreline. Fluency is like building a sandcastle. The finished product is made up of smaller sand structures, just like numerical fluency is developed through the pivotal understandings we will discuss throughout our sessions. A sandcastle requires connections between smaller structures. As you are building your sandcastle, you must consider the end goal so that you properly place the structures. Similarly, numerically fluent students must recognize connections between operations, pivotal understandings, and learning experiences. As teachers, we must keep the end goal in mind that we want students to develop a conceptual understanding of concepts, which will help us make important instructional decisions, such as where we should place certain activities to make the most impact on student learning and understanding. And depending on what you want your finished sandcastle to look like, you may spend a lot of time on your smaller structures, perfecting them, molding them, and decorating them. In the same way, students must have many opportunities, experiences, and time with our instructional approaches that we will share with you throughout the sessions. Fluency is not a one and done concept, just as an eye catching sandcastle isn't made up of only one small, perfectly decorated structure. And building a beautiful sandcastle takes time, just as building a numerically fluent student takes time. You also may have to consider the tide, sunset, and other beachgoers while building your sandcastle. This parallels fluency instruction as you will have to consider the pressures of instructional time and traditional mathematics instruction. And despite the obstacles, seeing your finished sandcastle is an amazing feeling. Likewise, seeing your students become numerically fluent over time as a result of best instructional practices is an amazing feeling. We want you to keep the metaphor of this sandcastle in mind as we move through our time together. Each piece of information will be a small structure as you build your own fluency sandcastle. One of the structures we're going to visit today is a number talk. You may be familiar with the number talk and the structure of how one works. Today, we're going to focus on using number talks to build fluency and instructional moves that make number talks effective. If you want to take a step back and read a bit more about the routine of a number talk, you can access that information in the travel itinerary of your journal. All right, let's dive right in. Okay, I'm going to show a series of 4 images, and Renee is going to share her thinking for each image, and then I will record her strategies as she shares them. So, Renee, are you ready to put your student hat on?
Absolutely.
Okay, here we go. So, I'm going to show you the first image, and I want you to decide, do you agree or disagree, or is this statement true or false?
I disagree.
Okay, why do you disagree?
Well, there are 3 beach balls and 4 beach balls. And if I count those, I get 7. So if I count the beach balls on the other side of the equal sign, I get 8. So they're not equal.
Okay, so how did you count? You knew there were 3 in the first circle. So how did you count to get 7?
Well, I saw 3 in the first circle, and then I counted up 4, 5, 6, 7.
Great. And then how did you see the beach balls on this side of the equal sign?
Well, I saw 4 on the top row,
Okay.
and then the same amount on the bottom row. And then I know that 4 and 4 more is 8.
Awesome. So you know that if there are 7 on this side and 8 on this side, that 7 and 8 aren't equal.
Right.
Do you agree with that?
Yes, because 8 comes after 7.
Awesome. I love how you clarified that. So you would disagree with this statement.
Mm-hmm.
Okay. So let's try another one. So same thing. I want you to think about, do you agree or disagree?
This time I agree.
Okay, why?
And I agree because there are 5 balls and 5 balls on one side, and I know that makes 10. Then on the other side of the equal sign, I counted and I got to 10 again.
Okay, so how could you prove that 5 and 5 makes 10?
So in my head, I thought about a 10 frame, and I know that there are 5 boxes on top and 5 boxes on the bottom.
Okay, so let me represent that. So if you had the 5 beach balls from the first circle here and the 5 here from the second circle, then you would have 10. And we can prove that with the 10 frame.
Right.
Okay, so how did you count the beach balls on this side?
So in that first circle, I saw 2 on the top.
Okay.
Then I went down and saw 2 on the side. And then 2 on the other side. And then 1 in the middle.
Awesome. So how, I didn't see it that way at all. So how did you count these when you saw them as 2s?
Well, I actually counted them by 2s. So I saw like the first 2 and I said 2, and the next 2 and I said 4. Then I said 6. And then I counted on from 6, 1 more, and that was 7.
Awesome. I did not see it that way at all. Great job. And then how did you count these?
And then from there, I held 7 in my head and I went 8, 9, 10.
Awesome. So we have 10 over here and 10 over here. So you said you agree with this one, right?
Yes, because there's the same number of beach balls on both sides.
Great. So both sides are the same amount, right?
Yes.
They look a little bit different, but we know that the amounts are the same. So let's circle true. All right, I'm going to show you another one. Are you ready?
Yep.
Doing a great job explaining your thinking. So this one's a little bit different. So if we wanted to make both sides the same amount, like this image, how many beach balls would we need to put in the circle?
7.
Okay, how do you know?
Well, there is 3 and 4, and I know that's 7 from the first side picture.
Nice.
So I would need to put 7 beach balls after the equal sign, so on the other side of the equal sign, to show that.
Okay. So let's go ahead and do that. I love how you used the other image to help you. So 3, 4, 5, 6, 7. Okay. So you said we would have 7 on this side now. So how many do we have?
7, 8, 9. Wait a second. That's not the same. I have
Okay,
too many.
so you said 7, 8, 9. So now you're thinking that's not the same.
I have way too many.
Okay.
So
how many too many do you think you have?
No. 8, 7, 9, 8, 7. We need to take 2 away.
Okay, so where should we take the 2 away from? This circle or this circle?
Let's take the 2 away from the ones that I was thinking and drawing on.
Okay, so what happens when I take those 2 away? How many do I have now?
5.
5, nice. So how can we prove now that this side has the same amount?
So we knew that 3 and 4 was 7 from the other side. And now I know that 5 and 2 is 7 because 5, 6, 7.
Nice. 5 plus 2 equals 7. That's not the best 2. So 5 plus 2 equals 7. So you agree now. So I'm going to cross off the 8 and 9 and you count it up. 5, 6, 7. Way to stick with that. All right, one more. Are you ready?
Mm-hmm.
All right. So how many beach balls could we put in each circle to make this equal?
So there is 9 that I can see.
Okay. How do you know there are 9?
Well, like one of the last pictures, I see 4 on top and the same amount on the bottom.
Okay.
So 4 and 4 is 8. And then one more from 8 is 9.
Nice job.
So I need to get 9 on the other side.
Okay. So what strategy might you use to get 9 on the other side?
Well, I knew that 8 and one more was 9. I could put 8 in one circle and 1 in the other circle.
Okay, let's do that. 1, 2, 3, 4, 5, 6, 7, 8. And then we would have 1 here.
Mm-hmm.
Okay, so we have 8 plus 1, whoa, equals 9. Okay. So I love how you used what you already know about this side to help you. Is there another way that we could sort these beach balls to make 9 on this side?
Well, I could move 1 over and make 2. So take 1 from that one from the other circle.
Okay, so if we took one of these beach balls and just moved it here.
Yep.
So now it's no longer in this circle. So now we have,
So now I have
how many in the first one?
yes. So 1 less of 8 is 7. So I would have 7 and then 2.
Nice job. And that equals 9. So you, it sounds like you were thinking that even if we move these balls from circle to circle, we're still going to have the same amount of balls in total here. So you know that you could keep moving those over and moving them around and you would still have 9. Nice job.
Can't keep adding them. I'd have to use what I have.
Nice job. Thank you for sharing your thinking. Now let's take our student hats off and slip on our teacher hats and dive into one of our pivotal understandings. The string of images displayed in this number talk were designed for students to access pivotal understanding 8, equivalence and equations, and the meaning of the equal sign. Many students have a rote understanding of the equal sign and identify it as a symbol to show an answer, rather than a symbol that indicates equal quantities. These images allow students to visualize and conceptualize equality. Your resource book gives the example of 3 plus 4 equals blank plus 2. How do you think your students would fill in the blank? Take a second to think about it. Surprisingly, many students may put 7, 9, or some other incorrect quantity based on their misconception of equality. So how do we clear up this misconception and help students gain an understanding of equivalence? Students need many opportunities balancing equations using concrete materials. Using true-false statements during number talks can also help to build this understanding. With these statements, students must determine if the quantities on both sides of the equal sign are true and justify their thinking. Some examples of this can be found in your resource book on page 17. The recording of student strategies by the teacher during number talks is also critical. Look at the example shown here. You can see two different recordings of the same student thinking for 258 plus 126. The example on the left can create misconceptions with students because based on what we know about equality, this would mean that 258 plus 100 is equal to 358 plus 20, which is equal to 378 plus 2, and so on until the equation ends. We know that this is not true. The example on the right would be a more precise, accurate way to record student thinking. It is crucial that teachers do not string together equations that are unequal, creating and solidifying misconceptions for students. So, keeping this pivotal understanding in mind, we want you to find your own images for a number talk that would help students conceptualize the understanding of equality. The images you choose could showcase mathematical tools such as 10 frames, place value blocks, or reckon recs. Go ahead and pause the video now, pack up and surf over to your digital journal to add your images. When you're finished, come back and join us for some more fun in the mathematical sun.
Welcome back, Mathcationers. Take a moment to read this quote. As we learned on our excursions so far, word problems are an integral component of fluency development. As students engage in word problems, they are constructing and applying mathematical ideas. In just a moment, you will pack up and head over to your digital journal to solve a word problem. When solving the problem, you may choose to use any of the options listed. Be sure to represent your thinking visually and numerically, and as you solve, consider relationships between numbers and mathematical concepts you are using. If you left your manipulatives at home, don't worry, we have a few packed in your journal for you. Welcome back, Mathcationers. When solving the story problem, depending on your solution pathway and the numbers that you chose, there are different relationships that you may have experienced. Choose a number is an instructional strategy you can use when implementing word problems. When students have the opportunity to choose a set of numbers or a number to solve, this allows them to be the decision maker and the thinker. When using this strategy, it's important to consider the purpose of the problem, so that this can help determine the numbers or the type of problems students will use. In their solution strategy, you'll be able to see how they made sense of the numbers and the relationships they use, such as a derived fact, place value, or a property of operation. When determining the numbers to use and choose a number, consider creating sets of numbers that have a commonality. For example, doubles, doubles plus one or two more or one or two less, making a 10 or making a 5, or composing and decomposing numbers. When solving this problem, there are many different types of relationships that students could encounter. Some of these relationships you may have explored were using repeated addition, skip counting, counting on, counting all, or even addition and subtraction. Constructing these concepts through word problems allows students to use and understand the relationships between operations. This is a key component to fluency development. If students understand how operations are related as they build their knowledge of facts, this can significantly reduce their cognitive load. As students work to make sense of word problems, they unpack a problem in order to determine what strategy they will use to solve. Carpenter and Levi state that one of the biggest challenges in unpacking a word problem with students is that you, as the teacher, can end up doing all of the mathematical work, and it is easy to lead students through a problem in a way that provides students a specific strategy to reach an answer. The goal, however, should be to support sense-making around the context, and to not help students come up with a strategy or an answer. As we support students in sense-making, we must shift from helping them focus on keywords in the problem that indicate how a problem can be solved to really thinking about the strategies or thinking about what is happening in that problem. When students are taught keywords or told what rule or strategy to use to solve a problem, this hinders the problem-solving process and the ability to make connections. So, what has the research shown? It tells us that often keywords or phrases in a problem suggest an operation that could be incorrect. Or students may use an alternative operation to make sense of the problem, and that is okay. So, let's dive into another pivotal understanding. Language of operations is a critical connection to student fluency development. This pivotal understanding is supported through word problems and problem-solving activities as students act out, storytell, and explain their reasoning of problem situations. It's through these instructional opportunities that students can build an operation sense and enhance their language of operations. This pivotal understanding can be closely connected to the mathematical practice attending to precision. At the core of this practice is the student's ability to adequately use mathematical vocabulary precisely and accurately during the problem-solving process in their justification and reasoning.
Now that we've spent some time swimming in this idea of numerical fluency through the lens of story problems and number talks and how they connect to a few of the pivotal understandings, we need to take some time to put our snorkel away and reflect. So, in just a second, you will head to your digital journal to do some reflecting. We would like for you to read a few pages from your resource book and make connections between the reading and the chart in your digital journal. As the session draws to a close, go ahead and stop the video, pack up, and swim over to your digital journal for the final time today. We would like you to do these before heading to session 2 because they will help with your learning as you move forward. We will continue splashing around in these ideas during session 2, so be sure to bring your flip-flops.